Servo Motors Explained Beginner's Guide to Servo Motors in Automation. Have you ever wondered how robots can move with such incredible precision, as if they have a brain of their own? Or how CNC machines can carve metal so accurately that they can cut hair-thin patterns into steel? Maybe you've seen camera gimbals that stay perfectly level, even while you're running or riding a bike. Behind all these modern marvels is one powerful yet compact device: the servo motor. This little motor is the unsung hero of modern automation, robotics, and precision control systems. In today's beginner-friendly guide, we're going to break down everything you need to know about servo motors, how they work, where they are used, and why they are absolutely essential in today's world of smart machines and industrial automation. Whether you're a student, an engineer, a hobbyist, or just someone curious about how things work, this video is for you. What is a servo motor? So first things first, what exactly is a servo motor? A servo motor is a special type of motor that allows for precise control of position, speed, and acceleration. It's not just a motor, it's an intelligent, feedback-driven system. It's called a closed-loop system, which means it's constantly checking its position and adjusting itself to make sure it's exactly where it needs to be. Think of it like this. A regular motor just spins when you apply power. That's it, no questions asked. A servo motor, on the other hand, doesn't just spin randomly. It moves to a specific position, speed, or angle, and then it checks if it got there. If not, it corrects itself in real time. That's what makes servo motors perfect for jobs that need accuracy, repeatability, and stability, like robotics, CNC machining, and automated packaging systems. The basic components of a servo system. Let's break down the three main parts that make up a servo motor system. To truly understand how a servo motor delivers such precise and intelligent movement, we need to look at the three key components that work together as a team: the motor, the sensor, and the controller. Each one plays a critical role in this closed-loop system, and together, they create the magic of smart motion. 1. The motor, the muscle of the system. This is the component that physically creates the motion, the part that actually moves the mechanical load. Think of it as the muscle of the system. The motor can be either AC, alternating current, or DC, direct current. AC motors are typically used in industrial and high-performance applications. They are powerful, durable, and capable of high-speed operation. DC motors, on the other hand, are common in smaller, lighter-duty applications, like RC cars, basic robots, and educational tools. Regardless of the type, this motor spins the shaft that connects to whatever you're trying to move, whether it's a robotic arm, a conveyor belt, or a camera platform. But here's the thing, the motor itself doesn't know where it's going. It just follows commands. That's where the next component comes in. 2. The sensor, the eyes of the system. The sensor is like the eyes and ears of the servo motor. Its job is to constantly monitor the motor's position, speed, or angle and send that real-time information back to the controller. There are two main types of sensors used in servo systems. Encoders. These are digital sensors that provide highly accurate position feedback. They are commonly used in modern, high-precision servo systems. Potentiometers. These are analog sensors often used in simpler or low-cost servo motors, especially in hobby and educational settings. Here's how it works. Let's say the motor shaft is turning. The sensor keeps track of how far, how fast, and in which direction the shaft is moving. If the motor is supposed to be at 90 degrees, but it's only at 84 degrees, the sensor detects this and informs the controller. This continuous stream of feedback is what allows the system to make fine-tuned adjustments instantly. Without the sensor, the system becomes blind and you lose the precision and intelligence that makes servo motors so powerful. 3. The servo controller, or driver, the brain of the system. If the motor is the muscle and the sensor is the eyes, then the controller is definitely the brain of the operation. The controller is responsible for making real-time decisions based on the feedback it gets from the sensor. Here's what it does. It receives a command from the outside world, like move to 90 degrees. This is called the set point. It compares this set point with the actual position reported by the sensor. Based on the difference, it calculates what action the motor needs to take to reach the desired position. That could mean speeding up if it's lagging behind, slowing down as it approaches the target, reversing direction if it overshot the mark, or stopping entirely once it hits the exact position. All of this happens in a loop, thousands of times per second. This is what we call a closed-loop control system. It's this ability to constantly compare, correct, and control that gives servo motors their signature precision. Without the controller, the motor wouldn't know where to go, and the sensor's feedback wouldn't be used. But together, all three components work in harmony to deliver accurate, repeatable, and smooth motion. In summary, the motor moves the load. The sensor tracks its position. The controller decides what to do and how to do it. This powerful trio is the secret sauce behind every high-performance servo system, and it's why servo motors are trusted in everything from industrial robotics to delicate camera gear. How does a servo motor work? Let's go through a simple example. Imagine you tell the servo motor, move to 90 degrees. Here's what happens. The controller sends a command to the motor, go to 90 degrees. The motor starts rotating. The encoder measures the position of the shaft, let's say it gets to 85 degrees. The controller says, not there yet, keep going. The motor goes a bit further, maybe it overshoots to 95 degrees. The controller then says, whoa, too far. Move back slightly. This feedback and adjustment loop happens in milliseconds, over and over, until the motor locks perfectly onto the target position. This is why servo motors don't just move, they know exactly where they are and they correct themselves instantly. Types of servo motors. Not all servo motors are the same. Let's take a quick look at the main types. 1. AC servo motors. Used in high-performance industrial applications. Handle high speeds, heavy loads, and long duty cycles. You'll find them in robots, CNC machines, conveyor systems, and automated assembly lines. 2. DC servo motors. Simpler and less expensive. Ideal for low-power, small-scale applications like RC cars and planes, DIY robotics, educational kits. 3. Positional rotation servos. Can rotate within a fixed range, usually 0 to 180 degrees. Used in robotic joints, grippers, and pan-tilt camera mounts. 4. Continuous rotation servos. Can rotate freely 360 degrees in either direction. Perfect for wheels, conveyor belts, or steering mechanisms. Your choice of servo depends on how much precision you need, the torque required, and whether you need rotational control or full rotation. Where are servo motors used? Servo motors are truly everywhere, especially in automation and robotics. Let's explore some real-world uses. Robotics for joint control, walking motions, and pick-and-place operations. CNC machines for cutting, drilling, and engraving with micron-level precision. Camera gimbals to stabilize footage by adjusting angles in real time. Electric vehicles and drones used in steering, throttle systems, and rotor control. Packaging lines for aligning products, sealing, labeling, and more. Aerospace in flight simulators, flaps, and control systems. Any machine that needs smart, controlled movement, there's a good chance a servo motor is inside. Servo motor versus stepper motor, what's the difference? Now, here's a common question. Should I use a servo or a stepper motor? Let's compare them. Stepper motor. Open loop, no feedback. Moves in fixed steps. Simple and inexpensive. Works well for light loads and basic movement. But can lose steps if overloaded, which leads to errors. Servo motor. Closed loop with feedback. Real-time correction. Smooth and fluid motion. Better for high precision, high torque, and fast-changing loads. Costs more, but offers much more reliability and accuracy. So, if you need smart, powerful motion, go with the servo. Advantages of servo motors. Let's quickly highlight some of the key benefits of using servo motors. High precision and accuracy. Smooth, quiet operation. Great torque-to-size ratio. Fast response times. Ideal for dynamic, repetitive, or high-load tasks. Long operational life when properly maintained. Disadvantages of servo motors. But nothing is perfect. Servo motors also have some challenges. More complex setup. Higher cost than stepper motors. Needs proper tuning of the controller. Requires regular maintenance in some applications. Still, in most industrial and high-performance automation systems, the benefits far outweigh the costs. Final thoughts. So, what makes servo motors truly special? It's not just about motion. It's about smart motion. Servo motors bring intelligence, precision, and adaptability into machines. They can measure, adjust, and hold positions with incredible accuracy, all in real time. Whether you're building a robotic arm, controlling a drone steering system, or designing the next-gen CNC machine, understanding servo motors unlocks a whole new world of automation possibilities. Thanks for watching. If you found this video helpful, go ahead and smash that like button, subscribe, and turn on notifications, because here on the Control Brainiac, we make industrial automation simple, fun, and easy to understand. Got questions? Drop them in the comments. Want more videos like this? Let us know what topic you'd like us to break down next. Until then, keep learning, keep building smart, and stay curious.